Welcome back everyone to part 2 of GANs, where what we're going to do in part 2 is actually create the generator and then the discriminator. And similar to what we did in the autoencoders lecture, we can then join them together to create the actual generative adversarial network itself. All right, let's head back to the notebook and continue where we left off last time. Okay, here we are at the notebook where we left off last time. Now, the first thing we're going to do is create the generator and discriminator. They're separate models, and then we join them together into a GAN object. Doesn't quite actually matter which one you create first since we're going to be joining them anyways, but let's go ahead and start off with the discriminator since it's a little bit simpler than the generator. So what we do is recall during training, the first phase is we're actually training the discriminator. So essentially what we're doing is we're taking a batch of real images sampled from either the entire training set or our particular only zeros data set for faster training. And we take that batch of real images, and then we also take an equal number of fake images that the generator will be producing. And we end up setting the labels as 0 for the fake images and as 1 for the actual true real images. And the discriminator is trained on this labeled batch for then just one step, using what we'll see as binary cross entropy loss, because it's either correct or incorrect, 0 or 1. And then importantly, what's going to happen is the back propagation only optimizes the weights of the discriminator during that training phase. And we'll see that when we actually write our training loop after we create our batches. But first, let's just create the discriminator model. We say discriminator is equal to a sequential model. And to do this, I need to actually add in some imports. So let's go ahead and insert a cell above here. And let's do our classic imports. We'll say import TensorFlow as TF, and then import, or we'll say from, TensorFlow.keras.layers, import, and we'll be using dense. And since we're dealing with kind of 2D images here, we'll have to reshape them as well as flatten them. Now this is a very simple discriminator and generator that we're going to be producing because we won't actually worry right now about using convolutional layers. We'll actually just do this all with essentially dense layers. And then finally, we'll say from TensorFlow.keras.models import sequential. All right, so we have our imports ready to go. Let's create our sequential model for the discriminator, and then we're going to add a couple things here. We'll say discriminator, and we'll add in the first flatten layer. Because it's a 2D images, we need to flatten them. So the input shape it's expecting is a 28 by 28 image. Whoops, make sure that's a list here. So it's 28 by 28, and then we flatten it out. So that means we can then apply our dense layers. So all this discriminator is trying to do is this image real or not? So let's go ahead and add in some dense layers. We'll go ahead and just choose some arbitrary values here. We'll say we go from those 784 in the flattened layer to then a dense layer of 150. Activation is rectified linear unit. And then we'll add in one more layer here, a dense layer. Let's go ahead and add kind of 100 more neurons. Start bringing it down, rectified linear unit. And then if you want, you could add more and more layers to make the discriminator harder to fool. But this should be enough for our particular use case of this simple only zeros data set. So after this, what we're going to do is add in our final output layer, just labeling it here. So you can add more layers if you want, try to make the discriminator harder to fool. But eventually at the end, what you need is a dense layer with actually just one neuron. And it's one neuron regardless of how many digits you're actually working with. Because recall, we're not trying to classify digits as 0, 1, 2, 3, etc. All we're trying to do with the discriminator is a binary classification of, is this image real or is it fake? And if you're doing a binary classification, then your final output layer is just one neuron with the activation function of sigmoid. Okay, so there's our discriminator, and then finally we say discriminator, and we compile this with the binary cross entropy loss, because again, it's just trying to see if an image is fake or if it's real. It's not trying to tell, is it a 1, is it a 7, etc. Okay, so that's our discriminator. Pretty straightforward, just creates that sequential model. You can add in more dense layers. Obviously, the more complex your discriminator network is, the harder it is to fool because it should be able to have more neurons and be able to learn more. But again, kind of depends on what your actual data set is. And then let's go ahead and create the generator. All right, the first step in creating our generator is to actually choose the codings size, that is to say, the latent representation. And this is really similar to our discussion on autoencoders. Recall that autoencoders went from some number of features, and if we're doing it with this data, for example, 784, and then they kept going down to something like 150, keep going down to, let's say, 30, and then we expanded it back out. We went then back to 150, and then back to 784. So this is what we would do as an example. And essentially, we have to decide on what this middle number is. And this middle number, recall, is some sort of lower dimensionality encoding. So the actual generator looks a lot like this decoder part, where it's taking some sort of encoding and then expanding it back out to generate some sort of output that will try to fool the discriminator. So in our case, what's going to happen is the generator looks a lot like a decoder, essentially taking some number starting from some encoding size or coding's size, and then expanding it back out to generate an image that will then be compiled and passed to the discriminator to see whether or not it fools the discriminator. So you have to choose some sort of coding size, and there's no right or wrong answer here. It's essentially how low do you want to go inside of this decoder. And typically it should be a lot less than your original feature set. So our original feature set, recall here, is 784. If you make it too small, however, then there really isn't enough to start off with to actually learn from and generate images. So what we're going to do here is, since we have a pixel size of 784 pixels, let's go ahead and choose an encoding size of 100. That is substantially less than 784, but not so small where the generator is just not going to have enough to start off with as a latent representation. So again, this 100 kind of signifies what this 30 was. So we would go from like 100 to 150 to 784, etc. And our generator is essentially going to look like that back half of the autoencoder, the decoder part. So we choose some coding size. Recall, it should be less than the total number of features you're working with, but not so little that you really have nothing to learn off of. And it's something you can play around with and experiment. So you create this generator as a sequential model, and then let's start adding the layers to it. So generator, we add in some dense layer. We'll go ahead and match our first layer to our coding size, give it an activation of rectified linear unit, and then finally give it an input shape of the actual coding's size. So keep in mind, this 100, we technically chose it off this coding size, but it's not reliant on it. What is actually reliant on this first layer in your generator is the input shape. So you could mess around with this and expand this to immediately to 150 if you wanted to, but in our case, we're going to take this 100 encoding size, first layer encounters 100 neurons, and then we'll start expanding it back out. So let's make the next one 150. Again, this should feel really familiar because it looks a lot like the decoder from our autoencoder lectures. So we'll say generator, go ahead and add, I'm just copying and pasting here, another dense layer, but instead we'll expand it back out to 150. And if you want to try to make the model more robust, you can add more decoding layers. But in our case, we'll just take this here, paste it in, and let's go ahead and expand this back out to 784. The last thing we need to remember is our discriminator expects a 2D input as a 28 by 28. Our generator right now is just producing this flat vector of 784. So what we need to do is we need the generator to finally reshape its output to match what the discriminator expects, which is a shape of 28 by 28. And there's your generator. Okay, so we have the discriminator. Notice we compiled the discriminator, but we don't actually compile the generator. So instead what we actually do is we create our generative adversarial network as a sequential model, and we join together the generator and the discriminator. And then to start things off, what we say is the discriminator dot trainable. So you should notice it says trainable. That's an attribute of the discriminator itself. Set that equal to false. And then finally, let's go ahead and take our GAN and compile it. We'll go ahead and choose binary cross entropy as our loss. And you can use an optimizer, whichever one you want. You can use stochastic gradient descent and choose slower learning rate. We'll go ahead and just choose Atom here and compile it. So a couple of things going on that I want to mention here, specifically these two lines of the discriminator trainable equal false and the GAN as well as the generator. So a couple of things we want to really clarify here is the discriminator itself. Recall, regardless of how many different categories you have in your original data set, all it's doing is saying what is real and what is fake. So by definition, if it's only two categories of what's real, what's fake, doesn't matter if it's classifying, well, not really classifying, but determining whatever image data set, whether it's MNIST, people's faces, etc. This is a binary cross entropy loss because it's a binary classifier. Then the generator itself, the reason we're not compiling it is because later on we'll see it's only trained through this full GAN model. So that's the reason why we're not compiling the generator. And then the GAN model, you'll eventually realize that this full model itself is also a binary classifier. So it can then also use this binary cross entropy loss. And then finally, what's important here is the way Keras works. The discriminator should not be trained during the second phase. So what we end up doing is we make it non-trainable here by setting it equal to false. And we'll see how essentially these three lines of code all come together during our training loop. Because we really have a special case here of two models kind of pitted against each other to hopefully produce realistic looking images, we can't just use our regular .fit command. So coming up next, what we need to do is actually set up our batches for our training loop. Again, we have this set of two models. We've combined them. Discriminator is first set as trainable equal to false in order to compile it here. And we'll see how this all comes together in the training loop coming up in the next lecture. I'll see you there.